Do you have your mic on? Is it on?
Yeah.
Okay. Next speaker is Caterina Puca, who's going to talk about obstructions to compositionality. Please go ahead.
It's not working.
Sorry, what's not working?
Oh, okay. Fine. Thank you. Thank you to the organizers and to everyone being here. Today we're going to talk about obstructions to compositionality. This is a joint work with Emma, Fabrizio, and Bob. And basically, we developed a sort of machinery that detects where and how compositionality fails. So first of all, what do we all mean by compositionality? If you look it up on Google or on ChatGPT, even better, the first result that comes up is the definition of compositionality in formal semantics, so linguistics. And it basically says that the meaning of a sentence is determined by the meaning of its words and the way they're combined together, so their syntax. So in a way, the meaning of words comes prior to the meaning of a sentence. But even in the same community of linguists, there's already some people that think that it's quite the other way around. That is, the meaning of a sentence is somehow primitive, and context is crucial in distinguishing between a black metal fan by Honeywell and a teenager black metal fan. But who cares about linguists anyway? You could say that compositionality is what makes engineering possible. Whenever you have to build a large physical system, you compose smaller subsystems together, and you can reuse knowledge about each subsystem to reason about the whole. And you can also go the other way around, so you can decompose and test each subsystem independently before integrating that. And this is kind of what happens with modular programming, right? As long as interfaces between modules remain the same, changes to one module do not affect the other. So we all know that this is what makes debugging much easier. And then we're at ACT. We've heard the word compositionality quite a few times in the past few days. Most people, what they mean by compositionality is merely that there exists a rule of composition. So, for example, I've heard people saying that process theory is compositional just because you can stack boxes together. And then last year, to add to the confusion, Bob defined this Schrödinger compositionality, which captures basically the essence of quantum mechanics, you could say. Entangled states are an example. What is a system that's Schrödinger compositional because you cannot separate them. Okay, so this is what we call a mumbo jumbo. Everyone means different things, so let's try to clean up the mess here. So Montaigne was the first to think of syntax and semantics as algebras, mathematical structures, and meaning assignment as a structure-preserving map between the two, so an homomorphism between syntax and semantics. And this is kind of similar to what lots of people do at ACT. When studying open systems, you define a functor from a certain syntax, a theory of boxes, to a semantic universe where the properties are defined. And for us, in the rest of this talk, a fully compositional system will be a strong monoidal functor. These categories often take the form of either monoidal categories or bicategories. And so for us, this functor should be structure preserving. So now, you could argue this is yet another definition of compositionality that does nothing but adding to the mumbo jumbo. But we will see that this is not the case. It actually unifies all the perspectives we've seen before. So first of all, a strong functor is both lax and not lax, right? And if you look at the definition of the laxator, for the lax functor, for example, you could say that in a sense it describes a situation where you can go from parts to the whole. Not lax, the other way around. And in a strong functor, you have both directions, when one is the inverse of each other. So a natural question you can ask now is, how far is a not lax functor from being strong or monoidal functor? And this is a question that actually lots of people have been having for a while. It's been an open problem for 5 years. Fabrizio can tell you all about that, and including Jules Hedges as well. I believe since 2018, first ACT.
To my memory, since the first ACT, people were there as well.
Yeah. And so this is our proposed answer. Don't worry, it's just an outline where we'll go in detail. But the step one is basically observing the lax functor is strong, if and only if the laxator is iso as a morphism in the target category. But now, a morphism is iso in a category, if and only if it is terminal in the slice over the codomain. And terminality, in turn, can be split into two conditions, weak terminality and subterminality, which are weaker. And now, the answer to the question comes down to identifying obstructions to weak terminality and subterminality, which for us will be questions about elements of certain pointed posets. And we'll see what this all means in a second. So first of all, a bit of intuition. If you look at the definition of a weak terminal object, you could say that it's an object such that it's reachable by any other object in that category. So in the sense that there always exists a morphism that goes to that object. And in a sense, this is the analog of what happens in topology when you have path connectedness, right? You can fix a point x, and for every other point in that space, you have a path that reaches x. And this implies that the pi 0 in particular is trivial. And okay, but now since a morphism is split happy, if and only if it is weak terminal in the slice, well, this means that this analogy specializes to an analogy between split happy morphisms and path connected spaces. Fair enough, let's keep this in mind. And we can do something similar for subterminality as well. You could say that an object is subterminal if and only if for every pair of parallel morphisms in the sense that they have the same source and target, they're equal. So this is an analog to what happens when you have every two paths in a topological space that are homotopical, which implies that the pi 1 is trivial in particular. Okay, again, because a morphism is mono, if and only if it is subterminal in the slice, you can say that this analogy specializes to one between monomorphisms and spaces with pi 1 trivial. Okay, so you can put the two together and say that a morphism is iso, okay, if and only if it is split happy and mono, we all know that. And this is equivalent to that morphism being terminal in the slice. So terminality is a kind of directed version, directed along the directions of the morphisms in that category, of the property of the space to be simply connected. So with both the topological invariants trivial. So the idea in this talk would be to follow this topological analogy, making it formal, and define invariants that can detect obstructions to terminality, just like pi 0 and pi 1 in topology detect holes in a space, for example. So obstructions in a sense for that space to be simply connected. Okay, so the intuition for obstructions to weak terminality is the following. You could say that an obstruction is an object that cannot reach a candidate weak terminal object, right? And ideally, we also like some kind of order relation between obstructions, such that if you have a morphism from one obstruction to the other, then you could say that the first obstruction is more fundamental than the second. And if you have two morphisms between two obstructions in the two directions, you would want these obstructions to be equal. So how do you formalize this? You take the poset reflection of a category, which is the image under this left adjoint to the inclusion functor of the category of posets into the category of categories. And this basically means that a weak terminal object will be the greatest element in the poset reflection. So this is the first ingredient we need in order to build our first invariant. And the second ingredient will be the quotient of an object by morphism. So whenever you have a category with pushouts and a terminal object, given any morphism, you can build the quotient of the codomain of that morphism by f, by the morphism, by taking the push out of f and the exclamation mark map, which exists by definition of terminal object. And this, under the same hypothesis, defines a functor from the arrow category of C, which is just the category that has morphisms of C as objects and commutative squares as morphisms, and the pointed category of C, which is the co-slice of the terminal object. And this functor basically sends every morphism to this pointed object, pointed with this map, which we call x in square brackets. Okay, even more interestingly, if we have two categories, both with pushouts and terminal object, and a functor that preserves them, you have this commutative square of functors, which basically involves the quotient functor and arrow and pointed versions of f. And this specializes to this commutative square whenever C and D are cat and pos. So we can have a quick sanity check. Both cat and pos have limits and co-limits, so in particular they have pushouts and terminal object, and the poset reflection functor preserves them. So this square exists, and it's commutative. And so we're ready. We have everything to define our zeroth homotopy poset, which will be this pointed poset, which we get by applying the functor from the arrow category cat to pointed poset to what? To the slice projection functor, which is an object of the arrow category of cat and correctly returns a pointed poset. So an object of the target category. So because the square is commutative, we can get this functor following either side of this commutative square, right? But because quotients in pos are simpler to compute, we chose the left-hand side of the diagram. And so we apply the poset reflection to this functor, and we get an order-preserving map between posets. And then we apply Q, which produces the quotient of the poset reflection of C with all the elements of the image of the poset reflection of DOM identified to a point, which we call x in square brackets. And so the image is defined like this by definition of the functor. And so it's very clear now why the pi0 structure is this one. An element is either the trivial abstraction, what we call x in square brackets. It basically collects all the non-abstractions, and y, the poset reflection of y, such that there's no morphism from y to x. And the order relation is defined as follows. Bit of intuition. The first is just that the order relation is reflexive. The third basically says that x in square brackets is minimal. And then the poset reflection of y is less or equal to poset reflection of z, means that, well, the elements that were not touched by the quotient are in the same relation that were before, taking the quotient. Okay, so now the pi0 captures precisely the intuition we had at the beginning. So it qualifies failure of an object to be weak terminal because it is trivial in the sense that it's only equal to the trivial abstraction if and only if x is weak terminal. This specializes also to qualifying failure of a morphism to be split epi. It is enough to compute pi0 of the slice on a different category. Okay, weak terminality or fixed here, we can now turn to subterminality. So an object fails to be subterminal when the arrow to that object is not unique from any other object of the category. So we can describe abstractions to subterminality as pairs or parallel with the same source and target but unequal arrows. So intuitively what we need here is the definition of the category of parallel arrows, which has objects as pairs of morphism, parallel morphisms that go to x, and these two commutative triangles as morphisms. But the cool thing here now is that subterminality can be recovered from weak terminality, because an object is subterminal in a category if and only if the couple of identities in that object is weak terminal in the category of parallel arrows. And this actually simplifies lots of things, because now the definition of the first homotopy poset is exactly what you would all expect, is the definition of pi0, because we're again qualifying weak terminality, but on a different category, the category of parallel arrows. So this is, if you think about it, again, this is analog to what happens in topology when you define the pi1 in terms of the pi0, and the category of parallel arrows in a sense replaces the space of loops, and the couple of identities replaces the trivial loop. I won't go over in detail the pi1 structure, it's just the pi0 structure, but computed on a different category. Again, pi1 qualifies failure of an object to be subterminal this time, because it's trivial if and only if the object were, and it also qualifies failure of a morphism to be mono. The two put together now qualify failure of an object to be terminal and failure of a morphism to be iso. So this is exactly the answer we wanted. So let's look at some examples now. Simple one, we're in set. We have this map of sets, set 0 to 0, 1 to 1. And we want to qualify failure of this morphism to be surjective, because this is what it means for a split epi morphism in set. And you could prove that this poset is actually isomorphic to the power set of the codomain of F, quotiented by the image of F. So the order relation here is the partial inclusion of sets. And in this case, in this example, the homotopy poset looks like this. You have the trivial abstraction to surjectivity, which is obviously the empty set, and what we sometimes call the minimal abstractions, the elements that are right above the trivial abstraction, are 2 and 3. So they're exactly the elements that are not touched by the image of F. And in a sense, they're the building blocks of all the other abstractions, because you can see they are contained in all the other ones. So does this tell us something we didn't know before? Absolutely not. But it helped us definitely understanding what abstractions will look like in a familiar setting like set. Okay, these homotopy posets are actually nicer than they look because they satisfy functoriality. So this assignment, in a sense, every object to the posets actually extends to a functor. And this is natural. So if you have a functor, this induces a natural transformation between the invariance functor and the respective position and identity. More interestingly, and this is not simply a consequence of functoriality, if you have two functors and a natural transformation between them, you could ask, okay, are the invariants associated to different components of the natural transformation related in some way? Because they're both morphisms in the target category. And the answer is yes, the answer is covariance. It says that this assignment, that sense every object to this poset, actually extends to a functor. And the intuitive consequence of this is that morphisms of C induce a kind of flow of abstractions to the components of alpha, under which flow you could think that a non-abstraction can never be trivialized. It's always sent to another non-abstraction, and this is by definition of a map between pointed posets. They must always preserve the base point, which is always the trivial abstraction, but a non-trivial abstraction may be trivialized. And we could look at covariance in action in a more concrete example, which is also an example of why failure compositionality is a bad thing. So open graphs are a bicategory where objects are sets, morphisms are open graphs, and two morphisms are interface-preserving graph homomorphisms. And rel is notoriously bicategory, and you can define a functor between the two that sends every open graph to its reachability relation. So how is it defined? Capital xy belongs to the reachability relation of a graph, if and only if there's a path from the input vertex x to the output vertex y. And this functor is lax. We can look at a specific example why it is lax. You can imagine that these three graphs, right? The reachability relation of the first graph is just the capital 1, 1, path from 1 to 1. Reachability relation of the second, capital 3, 1. And then the third graph is the composition of the first two graphs. And its reachability relation is the total relation. But composition of the first two reachability relation, which are the paths of the third graph, is the empty relation. So one is contained in the other, or vice versa. So this represents a problem, a computational disadvantage, you could say, because you could not deduce the reachability relations of parts of a graph from the whole. So by covariance, in this specific example, we have these posets, which are defined, again, which covariance here is applied to the functor that exists by definition of bicategory. And here they're applied to this laxator component, which is just an inclusion of relations. And in this case, because this is always an inclusion, so it is mono, this is injective, right? In the target category, pi1 is trivial. And the compositionality gap is only tracked by pi0. And in this case, the only non-trivial abstraction is 1, 1. It's a very simple example. But there are other times where compositionality, failure compositionality is actually good. And this is the case with Schrödinger, right? Schrödinger compositionality describes, again, all the situations where you cannot decompose something in a trivial way, in its parts. So entangled states are an example of that. And you can define, given any monoidal category, you can define the state functor, which sends every object of C to the state, a state on that object, which is just a morphism from the monoidal unit to that object. And this actually preserves monoidal structure. So it lifts to a lax monoidal functor. The laxator component sends every couple of states to their tensor product. And by covariance this time, we have these posets, which this time are simple to compute because they're in set, right? I won't go over in detail, but you can see that the minimal abstractions in pi0 are exactly non-separable states in A tends to B. This is intuitive if you look at the definition of the laxator. And the minimal abstractions in pi1 are all those pairs of states that get sent to the same tensor product. So covariance here implies that you cannot entangle a separable state just by performing local actions, because a trivial abstraction is always sent to another trivial abstraction. So a separable state must always go into another. And so, wrapping up, we have developed invariants that detect failure of terminality. That is also the failure of a morphism to be iso. that in turn qualifies failure of a functor to be strong, and so failure compositionality. So what we got is a more fine-grained, a more detailed analysis of why and where compositionality fails, than simply yes or no. It is compositional, it's not. So what we're looking in the future is more structured example and just set that hopefully have manageable combinatorics. And in a longer paper, we're also working on criteria for the existence of joints and meets of abstractions, induced monoidal structure on the posets, and more on functoriality. And that's it.
Okay, thank you very much. Time for questions. All right, let's start from the left.
Hi, thanks for a nice talk. I've been wondering, so you could choose to do like the duals of these constructions, or equivalently do these constructions on the opposite of a category, and you'd get things in terms of like initiality and co-slice categories and things. And that presumably should also be able to characterize obstructions to be an isomorphism. Do you have some sense for why the presentation in terms of the slice and the terminal is more preferable to the co-slice and the initial, or like?
It's just a choice, honestly. It was a choice to present the paper following terminology. So, but you can do, all the results are dual, so you can reason.
Right, but in like practical examples, have you computed them in both directions and seen whether one tends to give better answers than the other?
All the examples we worked on were with terminology, but yeah, we'll be looking at examples with initial as well. So
okay.
Future work.
All right, more questions? Yes.
Thanks a lot. I think this is a really good idea. These things work so well in algebraic topology because there's a huge toolbox of compositional tools for computing them on spaces. Any preliminary ideas at all about what happens if I compute these things on an amalgamation of categories or in a fibration or anything like that?
Actually, this work is related in some way with the theory of discrete vibrations, and we're working out the details in a longer paper, but yeah, it's a technical thing that is not, but definitely related.
Or something. Cool, thank you.
So I noticed that if you have a sequence of arrows and you perform this like push out against one repeatedly, then you can sort of map between the quotients because you're mapping into ones, and you get something that has kind of a similar feel to a spectral sequence, right? Because you keep mapping into these terminal objects. And so I'm wondering if you've thought about any connections with that kind of machinery.
Not yet, but that's a very good idea. Yeah, thank you. Happy to discuss it afterwards.
All right, any more in-person questions? No, seems not. All right, any online questions?
I have two naive questions.
Okay, yeah, Jorka?
First, regarding your topological motivation, if you begin with the path category of a graph or space and you apply your construction, is it clear that you go the whole circle, you go full circle and you recover what you had first? And second, what about higher homotopy groups?
Okay, I can answer the second question first. You can go higher, but the pi2, you could define the pi2 as the pi1 over the category of parallel arrows, but the couple of identities is always subterminal in the category of parallel arrows, so you would get a trivial one. So there's no point, but we can actually see, you could go into higher categories, and that may be a possibility that those may be non-trivial in there, but we're not touched yet that field. And your first question, I didn't really understand. So could you repeat it, please?
I mean, if you apply your construction to the case where the category C is the path category, say, of a graph, maybe within homotopy. Then would you recover? Is it clear that you recover the usual P1, P1, for instance?
I think so. Not really sure. Fab, can you?
If I understand the question correctly, you recover. If I understand the question correctly, you recover the quote unquote usual definitions of pi 0 and pi 1 when the category is a groupoid. So the point is that when your category is a groupoid and all the morphisms are invertible, then it basically, it pi 0 and pi 1 of like any object, they become the pi 0 and pi 1 of the groupoid in the usual sense pointed at that object. For categories of passive graphs, I don't know, honestly.
Yeah, well, this okay,
Yes,
was
it's,
a category which is not necessarily a groupoid, yeah. But thanks anyway, yeah.
is there a question there? Or yes, okay.
Two people have kind of mentioned this, and it comes to like back to an area called directed homotopy theory, where instead of like fundamental infinity groupoids, you take fundamental categories. And I believe this should actually align with the homotopy groups defined in that sense. And because this is effectively a two truncated directed space, that is why all your higher ones are, all your higher homotopy groups are 0. So I think there's likely an analog of this for the higher dimensions as well.
Thank you for the comment. I was about to ask exactly that. All right, any more questions? All right, any more questions from the online participants? Is that a raised hand? Okay, all right, then let's thank our speaker again.
Thank you.
All right, so for in-person participants, it's time for lunch. We will resume the talks this afternoon.